Hi, everyone. Welcome to the session on safeguarding SLAs and building resilient systems. A sneak peek to chaos engineering probes. Bit of intro. This is Saranya, and I'm a senior software engineer at Harness, and also one of the maintainers of LitmusChaos. And about my co-speakers, Amit and Vedant, who are also a senior software engineer at Harness and also maintainers of LitmusChaos, and Siddharth Vijay, who is AVP at engineering at Baazi Games. So, yeah, let's get into the agenda. So starting off with, we'll be giving a brief introduction to the three important terms, that is SLA, SLO, and SLIs. And then we'll talk about how SLAs affect the uptime of your system, and then how chaos engineering can act as a solution to this. And then we'll introduce resilience probes, which can be a powerful tool to assess the SLAs, and discuss about different types of probes and their use cases. And then Siddharth will be talking about how they are practicing chaos engineering and utilizing probes at Baazi Games as an adopter's point of view. And then lastly, some key takeaways. So without further ado, let's get started. Before going into the proper technical terms, I'm going to try to explain all these three terms in using a real world example. So as you all know that the concert season is going on all over the country, and considering you have got the tickets to the concert of a favorite artist, and if not, just imagine the scenario that a massive concert is going to be held, and thousands of people have already bought the tickets. And the promise is clear that the gates will open at 6 p.m. sharp, and the concert will be starting at 7 p.m. So this promise or the commitment that is made to you as the audience is known as SLA, or as a definition, it's the formal promise or agreement made with the customers. So now that we have got an idea about what is a service level agreement, let's get to the SLO. So on the day of the concert, from the organizer's point of view, they set a specific set of goals or objectives to ensure that everything runs on time and smoothly. So they set some objectives. For example, in this scenario, let's say a sound system should be tested and set up 30 minutes prior to the opening of the gates. That is by 5:30 p.m. And second, we can have another objectives like the gate systems should be operational and checked, and should be allowing 95% of the ticket scans to be processed within the 10 seconds. So these two can act as objectives to ensure that the commitment is the promise that has been made is met. And so this is the service level objectives. So now that we have defined the objectives, there should be certain indicators or something that can track the progress or performance of how if we are on track to achieve the goals. So this here comes the role of the SLI, or the service level indicators. So the example that I have mentioned, in case of sound systems, it can be like one of the indicators could be like time taken to verify each of the speaker and microphone. Or in case of the gate systems, it can be the average time it takes for the ticket scanners to process one single ticket. So these indicators can track the progress towards the objectives. And together, the SLO and SLI create a framework to ensure that the SLA is met and the event runs smoothly. So now that I have talked about, like, introduced these three terms as from a layman's perspective, now Siddharth will be talking about how they have set up these three concepts in Baazi Games. So yeah, over to you, Siddharth.
Hello. Sorry, thank you, Saranya, for that. Before I start, since we are talking about concerts, how many of you got Illuminati tickets? No one? Great. You know what I got? The room number. Error 404 not found. No, the Illuminati tickets. Cool, great. So my name is Siddharth Vijay. I'm Assistant Vice President Engineering at Baazi Games. So we make online real money games, Poker Baazi, Card Baazi, and Sports Baazi. Poker Baazi is our biggest vertical where we make online real money poker, which is used by players to play poker platforms. Since Saranya spoke about SLA, SLI, and SLO, which are the three most key contributors in terms of understanding the resiliency of the system, understanding the stability of our system, I'm going to talk about exactly what we were achieving as part of our SLA, SLI, and SLO in terms of our business perspective, in terms of our business requirement. So as you can see on the screen at SLA, our SLA in terms of keeping the uptime, and specifically, there are two major services that we work on. So since we are a game, the game core crust gaming engine is the basic thing because obviously the game will work only when the game engine is working. And the second most integral part of this system is the cashier service, which works and which takes care of all the monetary transactions. Because the money is flowing into the game, only then users are playing together. They're winning the money, they're losing the money. So that cashier service along with the game becomes a very integral and a very tightly coupled part in terms of business revenue. As part of the cashier service, what you can see on the screen is basically the SLA, SLO, and SLI that we have defined in terms of maintaining business and making sure that, there are minimum downtimes. So for service availability, we make sure that we guarantee almost 99.9% times uptime for the cashier service because obviously if the money is flowing in, only then the business is working. So we cannot afford even a single downtime when it comes specifically to the cashier service. So that is the SLA that we define. In terms of transaction success rate, obviously every user who's doing a transaction, we would want their transactions to be approved every time. But since transactions have multiple parties who play a role together, so there's a transaction provider, there's a service provider, there's a gateway, because of a lot of multiple parties, there's always a chance of something bad happening, some glitch happening. But we still ensure and we make sure that only 0.05% of transaction success rate failures goes in case of the total uptime. And if there is any failed transaction, we have internal systems to automatically revert those transactions. And we make sure as part of the refund timelines, so 24 hours is basically the maximum SLA that we have defined. But we always ensure that within a couple of hours, whatever money was deducted from the user's balance as part of a failed transaction gets refunded and accounted back to the user account. Now coming to SLA as part of service level objective. So the agreement is done. Now what is our objective that we are trying to achieve here? The objective, like I mentioned, is 99.95% uptime in terms of the cashier service I'm talking about. This is not with respect to the game. For the game, obviously, it is 99.099% because we cannot afford a downtime because it's a game service. The transaction latencies. Obviously, you all understand and we all come from the tech world and we understand the latencies for everything that we are working on. And imagine an application where we are getting millions of requests, almost 20 million requests every day. And then apart from those requests, a lot and a major chunk of requests coming on the cashier service for deposit as well as withdraw, even for check balances as well. So for those kind of services to maintain the uptime, another thing is very important to make sure that the latencies are not very much. So while we make sure that the latencies comes into and falls under the bracket of milliseconds, we have still defined a maximum period of 2 seconds as part of our objective. That even in the worst case scenario, maybe this is where we can stretch to in terms of a bad day or a bad technical issue. But apart from the glitch, we want to ensure and make sure that everything falls under the millisecond bracket. And then again, obviously, as part of the error rate objective, you can see 0.01% because technically and honestly, I can write 0.0 over here, right? Because there is nothing like 100% uptime in any system for that matter. And we all would agree to it. And so we also agree that we're going to make sure that even if it is per day rate request, per month, or throughout the year in terms of latencies or failed requests, we still say 0.0%, 1% of the total requests that we serve, which is a big number that I can't disclose right now, keeps as part of the error day. So error per day. Finally comes the service level indicator, which, like Saranya mentioned, is actually telling you or identifying that this is what we are achieving as part of our game service, as part of the cashier service, because both clubbed together are eventually helping us make the user come into the platform and play a game. So the indicators are, as we said, 99.95% uptime per month, and then accordingly as per the year also. The latency is less than 2 seconds, within milliseconds for 95% of the transactions, and error rate less than 0.01%. So all these three combined together actually defines the core SLA, SLI, and SLO of the cacher service, which becomes an integral part while a user is playing the game. And we are making sure that since we are dealing in real money gaming, we have to ensure that while the game is also up, the cacher service and the latencies as well as the SLAs are defined, and we are always adhering to it. I'll now ask Vedant to come forward and take it right from here. Thank you.
Okay. So now that we have gone through what are SLAs, SLOs, and SLIs, right? Let's look at how, we are only going to talk about SLOs. So let's see how it impacts our system when we are actually trying to keep it high, right? So here in this slide, we have, three categories, pointed out here. You could have many more. So we'll start with the first one, which is driving system design. So when we say we are trying to keep our SLAs high, right? What you would be thinking about is, let's say you have a microservice, right? And you want to keep its SLA as high as possible. You would be thinking about making it scaled and highly available. And when we say scale, right, you would be trying to keep it Okay. Yeah. So when we say that we are trying to keep it scaled, that means we are trying to have as much as, or I would say multiple replicas of a single service, right? And when we say sorry, not the for the scale one, right? Let's say today you have around 200 requests coming up for a particular service, right? But you can't actually say that would be the same thing tomorrow and day after tomorrow. It can increase 300, 400, right? So to keep it scaled, you need it to be automatically scaling based on whatever request traffic you are getting. To make it highly available, you would be trying to have, as I said, multiple pods for a particular service. Now, those are the simple microservices. You would be also having databases. For them, you can have high availability and scalability. But because they are the services which are actually keeping your data, you will also be thinking about implementing backups, right? And then coming to the last thing, which is network. You are already keeping multiple replicas of a single service. You also need to load balance the coming requests. That was on the system design. Now, if we now that we have figured out infrastructure, right? Now you can't be the one sitting in front of your screen and monitoring all of that the whole day. So you need a monitoring setup, and that's where we talk about operational practices, right? So your services are running, it's already scaled, and everything is really good, right? Now if something goes the other way, you're not going to see it all the day. You need some type of monitoring setup, and if you have that monitoring setup, you still don't want to see that graph going up and down for the whole day. So you need an alert setup. So if something goes down, you need a instant alert at the particular instance of time. Now, and like we are going in a story way. So let's say you got an incident. Now you need to manage that incident. It could be, if it, let's say in your organization you have multiple services, you would want to reach out to the owner of that particular service, and then it could go into debugging and everything. But while you are debugging it, you don't want your customers to be hanging out there, right? You need to let them know, okay, something is wrong. There is a maintenance window which we have open, and we are, currently fixing it. So that's where maintenance windows comes in. Now, we have the monitoring setup ready. Alerts are coming fine. We have the maintenance windows also ready. Infrastructure is good. All of this comes at cost. So that's where the cost considerations comes, right? Because if you are making it scalable and you are adding horizontal order scalars in case of Kubernetes, all of it is going to come at a cost. Now, that is a cost which you are incurring for your setting up your infrastructures. But if something goes down, you have your business and your customers are getting hit by that. So your business can get a damage. That's where the penalties comes in. Now, after that, finally, you have got an incident, you have fixed it, customers are happy. Next time, what do we do so that it doesn't happen again, right? We need to invest in reliability. We need to simulate those scenarios in our lower environments and see what is happening there, right? And once we have done that, we have simulated different scenarios. We also want to analyze whatever is happening there, because based on that, you can create your own run books, right? Because if next time same thing happens, and for the first time you took, let's say around, that's not ideal, but let's say you took 1 day to fix it, you don't want that to happen again, right? You want to fix it in maybe half an hour or 1 hour, right? So that can only happen once you have already analyzed your past downtimes. Now, lastly, with all of this, if you are managing the high availability, you are able to monitor your system, and you are already investing in reliability. What it does is it builds trust into your customers, and that's why we have written there highly SLAs, build trust. You have built the trust. Last thing which remains is, with all of this, in a particular process, this is something which you build as part of your organization, right? As a customer, let's say when they got hit by this incident, maybe they saw some issues, or they want you to change something in your own process. Maybe you gave them the maintenance window after the incident happened. Let's say 2 hours after that, they want it to be very rapid. They want you to let them know maybe like in next 15 minutes or so that they can plan for it, right? So that's where the feedback loops comes in, so that you can keep improving your whole process, right? So that was all about how, when you consider SLAs, how it impacts and influence your system, and makes it more robust. Now I will give it up to Amit.
Okay, thanks, Vedant. So I'll be talking about one of the solutions to keep your SLAs high. So as the screen shows, chaos engineering. So as the statement says, chaos engineering is a proactive approach to maintain and improve the system reliability by intentionally injecting fault in a controlled environment. So by doing this, you can identify the weakness in your systems, validate how much fault tolerance your system has got, and ensure that your system can withstand any unexpected disruptions. So in basic terms, break your things, observe and analyze, and then fix it. And this process continues until and unless your system is resilient. And as a solution, you have to identify your steady state conditions. So what are steady state conditions? These are basically the metrics and the behavior of your systems before any disruption happens. And once you have overcome all the disruptions, then you also check out those metrics. And this is how you identify the steady state conditions or hypothesis. Then you introduce a fault, and then you check if you have met the SLOs or not. If the SLOs are being met, your system is resilient. If not, then there is weakness in your system. Similarly, if there are weakness in your system, this loop continues until unless you have met all your SLOs. And now moving on to resilience probe, which this talk is all about. So for this, we are using LitmusChaos. And LitmusChaos has got a feature called as Resilience Probe, which actually helps you to safeguard your SLAs. So probes are basically some reusable, pluggable checks that you can use with your chaos experiments. It's not just about running the faults, but also to validate different things. For example, taking example of Baazi Games, for once they have injected a pod delete or pod network loss on their cache service, their leaderboard service should not go down. So with Resilience Probe, we can add those checks. We can call the HTTP URLs and see if the URLs are accessible or not. Going on the diagram is just very simple. You configure a Resilience Probe. You plan out the experiments with different faults, add these necessary actions or probes, schedule the experiment, run the experiments, and observe the impact on your system. So the different type of probes that we have with LitmusChaos are HTTP probe, as it shows querying health and downstream URLs. So you can check for response codes, you can check for response bodies, if they are meeting your standards, if the URLs are accessible or not. Those can be done using HTTP probes. Command probes is one of the powerful probe we have it in Litmus. So with this, you can use any of the command shell commands, or you can Dockerize your script, use it in the experiment fault, and it will do the thing that you have configured. And then we have Kubernetes probes. So as it shows, perform some CRUD operations. It will create or update or delete any of the Kubernetes resources when your system is under chaos. And lastly, we have the Prometheus probe. So if you have Prometheus set up as an APM tool, you can make some PromQL queries whenever your system is under chaos. For example, if I have a pod for which I have specified the threshold of memory as 50 M, but under chaos it exceeds 50M, then I can make an assumption that my system is not resilient, and depending on the result of these probes, it will actually tell if your system is resilient or not, or if the fault injection was successful or not. Not just these probes, we have different modes to execute these probes. So there might be different use cases depending on different users. So these probes can be run according to start of the test, end of the test, or if I want to observe these probes over the execution period, then I have these options of on chaos and continuous. And the edge probe is basically checking these actions before the start of the test and after the end of the test. So yeah, I'll now give it to Siddharth, and he'll actually tell how they are using resilience probes to validate the system resiliency in PokerBaazi. Yeah.
Thank you, Amit. So actually, before we start on this, I just want to quickly go back to this slide. And I want to ask a question to everyone here. How many Jerrys do we have in the room? No? Only 1, 2, 4? This is my team, ignore them. No Jerrys? How many of you have unintentionally made a blunder which led to a production outage? Okay. How many of you have intentionally made a blunder which led to a production outage? Okay. All of you can become good chaos engineers. And this is what chaos engineering is all about. This is what the crux of chaos engineering is, to become Jerry. You have to hammer yourself at every given point of time in every single hook and corner of your infrastructure, so that you know that at a bad day if something goes wrong, you know first of all where to find it, how to fix it, how quickly can you come back up, reduce your downtime, maintain your SLAs, and get promoted. Cool? Great. So my journey to LitmusChaos and actually to the entire chaos engineering ecosystem started a couple of years back. I read a lot of blogs, I write a lot of blogs, and once I was reading a blog about chaos engineering, it caught my attention. I started reading about it. I dig deep into what exactly it is, why do people do it, why is it necessary. I related that we have been doing these tests by ourselves at some given point of time. It's just that we didn't know we were actually doing chaos engineering. And when I actually read about it and understood the entire scenario, I mean, this is my 6th or 7th talk this year just on chaos engineering, because I loved it so much that I went on to it. I asked my team to make sure that you understand chaos engineering. We pick up a tool, we start implementing it, and we know that where all do we need to test it. Just so that, because our system being a gaming application has to be up all the time, we have to ensure that we cannot stop ourselves from going down, or we cannot stop any technical glitch to not happen. But what we can do is, if any technical glitch is happening, we know where to fix it and how quickly can you come back up. Correct? This is basically an ecosystem that we are building internally. It's kind of an internal platform, developer platform, IDP platform that we are building at PokerBaazi. And you'll primarily see a lot of CNCF tools over here: Kyverno, Litmus, Istio, Kiali, Fluentd, Argo. Why is that? Because when I started and when we started working on Litmus, we were so happy with what CNCF tools are providing us in terms of community support, in terms of open source projects, that we eventually started the journey and we brought in a lot of other tools into the system. And now we are actually developing an internal platform with the help of just these 7 CNCF tools to help us achieve what we are planning to do. Now, jumping back onto Litmus, since we are talking about Litmus over here. So these are some screenshots that I've added from our LitmusChaos experiments, and I'll now tell you exactly what we were doing and how we were doing it. So like Amit was mentioning about our cashier and leaderboard service. So leaderboard service is nothing but it's a part of our game. So whenever you're playing a game, there's a leaderboard which is calculating your rank, and when you win that leaderboard, you obviously get some money. Correct? So that's a part of the game service. Now, whenever that leaderboard is calculating the rank, and when you win something, you finally get it credited, and that transaction is happening via the cashier service. So now you understand the correlation between the leaderboard service and a cashier service. Both needs to work together for a single flow to happen, but both can independently also work together, and they need to work together. Because understand this case. See, if my leaderboard service is down for some technical glitch, if it is not able to calculate the rank, should it limit my user to add more money? Should it limit my user to withdraw the money? No. And similarly, if my cashier service is down, should the leaderboard also stop working? No, it's an independent thing which is calculating the rank based on the gameplay. You can withdraw or add more money whenever the cashier service can come back up, but at this given point of time, that should not block you from playing the game. So this way, in our ecosystem, a lot of services and microservices are very loosely coupled to each other, wherein they complete one single workflow, but as an independent entity, they can also work and they need to work, so that there is no multiple blockers coming in one single point, or one single point of failure. And that is what we were testing. And since I don't have much time actually, otherwise I would have given you 10 such more examples, what we are implementing. But this was the core crux and the most important example, and that is what I'm showing you over here. What you see over here is a Litmus dashboard that we have. I ran a test on one of our leaderboard surveys in which we deleted a pod. It's running on a Kubernetes cluster, and we deleted one pod on it. When the leaderboard service pod was being deleted, as you can see on the logs, we ran a parallel HTTP probe on the cashier service. So both, like I just mentioned, both are clubbed together but running independently. So on one side, the pod was getting terminated for the leaderboard service, and similarly, while the pod was deleting, so in probes you have the option of started at the end or the start, continuous probe like Amit mentioned in the previous slide. We ran a continuous 200 ping, obviously to the ping to the cashier endpoint, to get the HTTP status code 200. Correct? And this was continuously pinging the cashier service to tell us that, okay, for any reason, if in future our leaderboard service goes down, for any goddamn reason, we still have the cashier service up and running, which is not affecting the user from depositing or withdrawing the money. As that you can see on the screenshots right now. When we run the test, basically what Litmus does is, it will give you the option to integrate on your cluster in your namespace. You can select multiple options, create, delete a pod, fork the network, hog the disk space. There are multiple options that you have. And the good part is, they've given you such options which you generally don't think about it. I mean, how many of us would think that I will fork the network of my container or of my cluster? No. At max, what we can do is, I'll increase the CPU or the memory, I'll delete the disk, or maybe I'll run some scripts which can hack those, modify the JVM or things like that, correct? But hogging the network and such multiple other use cases, which are generally not very common in terms of implementing at our own end. But if actually they happen in the production environment, it will take you a while to first of all figure out that what has went wrong. Forget about fixing that at a later part. The first part would be to identifying the use case that what has gone wrong. Likewise, so when we were running the deleting the pod, for the leaderboard, as you can see over here, when we ran the test, these two leaderboard containers, they were running, and then finally the deleted pods, they again came back up. So like I said, when you run the test, it will delete that particular pod. You can define the time that, okay, for 5 minutes, 10 minutes, 15 minutes, I want to keep that pod deleted, so that in the meantime, I can run my probes, which will identify the dependency of my services. And once the action and the activity is completed, the container will come back up. So Litmus won't let you leave on your own. I've deleted the pod, now go do whatever you want. No, it will bring it back up. It will make sure that they have made you come to the same state from where you started the delete pod action. But in the meantime, you can test multiple other things which are clubbed together. Correct? Okay. So over here you see that the pods were deleted and then the pods came back up for the leaderboard pod. And over here in this screenshot, you can see the cashier probe which is running. So on the top of the line, if you see HTTP get method information response code 200, name cashier. I've hidden the URLs for obvious reasons. The cashier URL was continuously giving us 200, number of pods target 1, with a chaos interval after every 2 seconds it was checking 200, 200, 200 on the cashier service, making sure that the pod is deleted, and then the pod came back up, but cashier was still up and running. And finally, it told you, okay, the cashier probe has successfully passed. It has given you the checks of 200, what you have set up. You can add multiple checks, you can add multiple error codes, you can modify it accordingly. You can even modify it accordingly as per your use case for one container or for one service. And finally, when the probe is passed, you have ensured that these two services, in our case, as I'm explaining right now, the leaderboard and the cashier service. So while the leaderboard container went down and then it came back up, it made sure and gave us the confidence that our cashier service was still up and running. So one, kind of one forced implementation of something going wrong in the future in production, but we have checked that box because now we know that if something happens in this environment, our cashier is still safe. Finally, when the test is successful, this is what you see on the screen. Your test was successful or the leaderboard. It installed the chaos faults, pod delete, clean up chaos resources, whatever it has created, it will clean it back up. It will leave you to the same state of your namespace and your cluster. And on the other hand, as you can see, your continuous probe for HTTP on the URL that you can see on the logs as well is successfully passed, that we have run, one completed, giving us the resiliency score of 100%. So with this, what we have achieved is, we have started achieving not just with one example, with multiple other examples. We are trying to achieve a scenario wherein we know, like our engineers, our teams, all of us know that if something is breaking in the future, or if something which is not, we have imagined could go wrong at any given point of the infra, because obviously every infra is really huge these days. People have hundreds of clusters, hundreds of containers, nodes, pods, backend, front-end APIs, etc. and whatnot. Anything could go wrong at any point. So now we know that in such scenarios, the dependency of our services, the dependency of our APIs and microservices, how are they clubbed, how tightly or loosely are they clubbed, and are they affecting another or each other or not? Because sometimes what happens is, one thing has gone wrong, you're trying to fix it, but eventually the later repercussions are something else is failing because of it. And that takes a lot of time while you are debugging a production outage. With this, it helped us at Baazi implementing chaos engineering using Litmus Chaos to achieve that resiliency score. It's not that we have done it all. We are still learning, we are still growing, we are talking to the team, we are giving some feedbacks, we are helping ourselves, we are helping to the other community, so that all of us can implement Litmus Chaos in terms of creating the resiliency. Since being a gaming company, uptime is very important for us. That is all from my side. I now ask Vedant to come and finish off the slides. Thank you.
Okay. So now that we have seen, what Litmus Chaos can do, we can, simulate different chaos scenarios. We can do static, validations for your, let's say you have a coupled service or, individual services. So this slide is all about what's next for Litmus Chaos, what is coming in future. So as Siddharth was showing, right, we have a, chaos workflow which runs and injects chaos. So for that, you, deploy infrastructure into your cluster. What we are trying to do in future, we want to make that infrastructure transient so that it doesn't have to stay in your cluster for a long time. If whenever expand runs, it will go there, do its work, and come back. Next is K8s GPT integration. What we are trying to achieve with that is maybe generate some summary, whatever experiments you ran, or some recommendations on what you can do to fix your issues, or maybe generate the runbook itself for you. And then next is more SDKs. We have been getting requests from the community to generate more SDKs, be it Python, Java, and many languages. Similarly, other one is native chaos workflows. We want to create our own chaos workflow type. We have been using third-party tool for orchestrating our experiments. Next is Terraform support. We have been getting requests from community for support for Terraform to orchestrate chaos experiments, deployment of chaos infrastructures, and etc. And then finally, the main goal is graduation. That's we will have a party. So yeah. With that, thanks for being an amazing audience. You can check out Baazi Games. You can scan the QR codes. You can join our Slack channel if you have questions in future. You can check out our GitHub and start our repository. So yeah, if you have any questions, we can take it up. Yes.
I think that's okay. Doing chaos engineering is a costly business, I believe. That you spin up a controlled environment, and then you launch a lot of probes, and then you check whether it's tolerant or not tolerant. So what is the ideal budget to actually allocate for the whole chaos engineering situation? Like how many resources, what kind of infrastructure do we need to actually see that? Because it may vary when you have a large infrastructure, it may vary when you have a small infrastructure.
Mm-hmm.
Right? So how do you do that?
Okay, so firstly, let's say with respect to infrastructure, right, where you are doing chaos engineering, right, with respect to, let's say, Litmus Chaos, in your case, let's say you have a QA cluster, right, and there you would be deploying a chaos infrastructure. Now, to simplify that, I mean, let's say you in your organization you have multiple teams who have access to different namespaces. If you don't want to give them access to the whole cluster, you only want to give the access to the particular namespace for whatever they have already. In that case, you will have to deploy agent for different namespaces, and that's how number of pods are increasing. So your space is increasing, CPU is increasing, so your budget will increase. But let's say you want to be cost efficient, but you are good with giving access to different teams for the whole cluster. Then there is a cluster scoped agent. You only need to install one agent, which will do the chaos for your own one cluster, right? And let's say even with the cluster agent, let's say you want to achieve not all namespace you don't want to attack. Let's say certain 5 or 6 namespaces you have only want to attack those namespaces. You can deploy a chaos infrastructure, which is cluster scope, and update its permissions, and it will have access to those namespaces only. Right? Now, it all depends upon how many infrastructures you are deploying. So as part of chaos infrastructure, there are only 4 pods, which generally takes around maybe 20-50 millicore CPU generally. So it's fine, but yeah. So does that answer your question? Yeah.
Just adding one other point onto this. So from the infrastructure side, like Vedant mentioned, and it's more of a conscious call for the business. It's a business call as well. So like we are testing the cacher service. Why? Because if my cacher service goes down, it will cost me millions of rupees, right? For a 2-second downtime as well, correct? Now imagine for me, if cacher is going down, if there's something that I can prevent using chaos engineering, I don't think I'll even spend 1/10 of the amount that is being wasted as part of a production outage. Correct. So it's more of a business cost also. And then again, like Vedant mentioned, it's not that big of a setup that you have to run in terms of running these test scenarios.
Yeah, one quick technical question over here. Like you said, the LitmusChaos supports multiple different type of probes, correct? Like CPU, network, and whatnot, correct? I'm sure you are dealing with the HTTP one as well. So I just want to know, like in this HTTP one, do HTTPS as well for upstream? Like, we want to get some response like some 4502 or something like that, correct? Rather than 2xx, correct? From upstream, correct? So that we can handle those sort of scenarios as well in the case like upstream is down or something like that. Do LitmusChaos support those injections as well? Because just want to know that.
Yeah, so currently, as of today, we have HTTP probes, which you can use for simulating, let's say, response code or response body, but that is for HTTP. We have seen some requests for HTTPS yet, but, we didn't get much attention on that. Maybe, if we get, maybe more GitHub issues on that or Slack threads, we are happy to do that. There's no issue. We have done some POCs in past, so it's not like it's not doable. So we can do that. Not yet, yeah, and as of today, no.
So is there anything in the roadmap in the area of security chaos engineering?
Security chaos engineering.
So by security, you mean like implementing?
Basically, you are applying the chaos engineering to security side of your infrastructure. Is there anything in the roadmap in this chaos?
As part of like predefined faults, we don't provide, but there is a way. We have a chaos fault, which is BYOC. We have had scenarios in past with respect to, let's say, you have a chaos in cloud infrastructure, let's say load balancer or VM or anywhere, right? With respect to security, we have had some scenarios, let's say you want to update RBACs or, service account permissions and all, right? So for that, let's say in case it's GCP or AWS or any cloud infrastructure, they provide APIs for that. Now with BYOC, we give you the freedom. Whatever you want to do as part of chaos fault, you just need to give one image. You can write your own logic. So let's say in case of GCP, AWS, they provide REST APIs to manipulate their resources. In past, what we have done is, you can write a code, maybe Golang or anywhere, and you can call those APIs with proper permissions. You can update those RBACs, and you can have that image ready, and you can directly pull that image into the BIOC, and it will run as part of LitmusChaos.
You can extend the framework.
Correct, yeah. Any more questions? Okay. Thank you. Thanks, everyone.
Thank you, everyone.